Hi folks, welcome back. This is lesson 3 of the P4 topic, which is all to do with radiation and radioactivity and stuff. So this one is about nuclear equations, and I want you to be able to represent radioactive decay, radioactive decay using equations. So to start off with, there's 3 words on the screen there with blanks on them basically, and I want you to just fill them in from memory. Hopefully you remember from the previous lesson. So fill in what those 3 words will be. They're all different types of ionising radiation. After you've filled in those blanks, I just want you to then match up the type of ionising radiation to its description, and these are descriptions of each of the 3 different types there. So just pause the video, don't take more than 60 seconds on it, and see if you can fill in those blanks and then match up those words, those different types of ionising radiation, to each of the descriptions there. Okay, let's go through those then dead quick. So the first one is alpha decay, the next one is beta decay, and then finally we've got gamma decay at the bottom. So after you fill those in, I want you to match them up to the descriptions on the right hand side there. So that is the description of alpha decay. It's highly ionising, it exists as a large particle, which is 2 protons and 2 neutrons, and it cannot penetrate through paper. Then we've got beta decay, and that is partly ionising, less ionising than alpha. It exists as a tiny particle, which in this case we're going to, it's an electron, and it can penetrate paper but not aluminium. And then no prizes for guessing the last one. Gamma is very low ionising power. It exists as a wave, but it can penetrate through lots of materials. It's partially stopped by concrete and lead. You need a lot of them to like very thick lead, very thick concrete to actually stop it. Right, let's jump straight into it then. So why do things give out radiation in the first place? To find that out, we need to go on a bit of a journey right into the centre of an atom. Okay, so there's a diagram a bit like the one I showed you in a previous lesson. So let's just have a quick recap of what the parts are, or the subatomic particles that you find in a atom. Okay, so this is an electron, and it orbits around the outside of a nucleus, and this is the nucleus in the middle, and it's full of protons and neutrons. Don't worry too much about the colours, they're just to show that there's a difference between protons and neutrons. They're not actually different colours in real life. So these protons and neutrons make up the nucleus. I've also said again that previously that they're sometimes referred to as nucleons. So protons and neutrons, sometimes we call those nucleons because, well, the particles that are found in a nucleus. That's what we're concerned about when we talk about radiation. Okay, so this nucleus is where radiation originates from. It's not the electrons, you can kind of ignore those. So you'll see quite often in this topic, when I show you a nucleus, it's just a nucleus by itself. It's not a full atom, because we're not really interested in what the electrons are doing, because they're not really part of the whole idea behind radioactive decay. It's just the nucleus we're interested in. You can see a nucleus on the side there, full of protons and neutrons. Again, I've got rid of the electrons on this, I don't need to see those. And it happens to be unstable. You can see it's got energy because all the little particles inside it are moving, oscillating backwards and forwards. So this nucleus has energy. It's also worth noting this is a really big nucleus. Okay, so that is why it's unstable. The bigger a nucleus gets, the more unstable it becomes. So it's got lots of energy. Now let's just think about that. What would you do if you had lots of energy? I'm guessing you'd run around, jump around, do a dance, whatever you're going to do. And that is to expend some of that energy, to get rid of some of it. And that's kind of what the nucleus of an unstable atom would do as well. I'm not saying it's going to do a dance, but it's got a few different ways it could try and get rid of that excess energy, and we're going to talk about them in this little table here. Later on, when I start to refer back to a structure sheet, it's this I'm talking about. So you might want to rewind the video and come back to this. So there's 3 ways that it can get rid of excess energy. Okay, so a nucleus like this, it's unstable. There's 3 ways that it could get rid of excess energy. Nothing on this table is new to you, by the way. It's more of a recap than anything else. So it could undergo alpha decay, it could undergo beta decay, and it could undergo gamma rays. Okay, or gamma decay, I should say, give out gamma rays. Those are the 3 ways that it could get rid of some excess energy. Let's think about what the structure of each one of these things looks like. So if I've got a nucleus and I said, oh, it's just undergone alpha decay, it's just emitted some radiation in the form of alpha decay. What does that alpha decay look like? And it looks like this. So it's made up of 2 protons and 2 neutrons, and you can see them there in a little bundle. Quite often this gets referred to as a helium nucleus because it looks like a helium nucleus. If you look on the periodic table and you look at what's got an atomic number of 2, as in an element that's got 2 protons in its nucleus, you'll find that's helium, and this has got 2 protons in it. So we can refer to this as a helium nucleus, and we frequently do. So that's what's happened. So a nucleus like this, it's unstable, might give out 2 protons and 2 neutrons, or a helium nucleus, get rid of it, and that way the nucleus, after that decay, has got less energy, and therefore it's more stable. In beta decay, a neutron becomes a proton and an electron. So one particle basically turns into 2. After that, so I've gone from a neutron to a proton electron. What happens is the proton stays in the nucleus and the electron gets farted out, it gets ejected, emitted. And that is beta decay. So that little electron getting fired off is beta decay. Now that makes sense referring back to a previous lesson when we talked about types of radiation and how penetrative they are and how ionizing they are. Because if you think about it, 2 protons and 2 neutrons are massive compared to an electron. It's got a minuscule amount of mass. So we've got 1 neutron turning into a proton and electron, and the electron is what gets emitted. Okay, so that's why I've made the picture of the electron big, as if to point out that's what's being emitted. In the alpha decay, this is what's being emitted. That's why there's a big picture of it. Gamma rays, dead easy to remember because there's no particles emitted at all. It's just a wave. Okay, so gamma rays exist as a wave. Now, what I've done is, you don't really need to know the properties here because we've gone through them, well, a few times now, basically, but just as a nice little summary to put them all in the same place, I've stuck them in here. Okay, so alpha decay is the most ionizing and the least penetrative. Beta decay is partly ionizing and partly penetrative. And then we've got gamma rays, which are the least ionizing, but by far the most penetrative. Okay, they can only be stopped really by really thick lead and really thick concrete. So this, later on, when I refer you back to the structure sheet, this is what I'm talking about, okay? And I literally mean the structure, what is being emitted. That is really important. If you can remember that alpha means 2 protons and 2 neutrons leave the nucleus, and in beta decay, an electron leaves the nucleus after a neutron turned into a proton electron. That's the electron that gets ejected. You're going to be in a good position. You're going to understand what's going on later on. Gamma rays, no particles emitted at all. It's just a wave. So let's have a quick look at these in practice then. Okay, so I've got a something that might look familiar to you there. It is a element of the periodic table, and to be honest with you, you can ignore the letters here for the time being. I mean, we're going to use that later on, but what we're really interested in is the numbers. Okay. Again, quick recap, the numbers, when you see something like this on a periodic table, this at the top, the biggest number, I shouldn't have said at the top because its position is irrelevant, but the biggest number, 232, is the mass, and that is all the protons and neutrons added up. Okay, so if I said 232 is its mass, you know in total, if you take all the protons and all the neutrons and you stick them together, 232 is the number that you've got. The smaller number is the atomic number, and atomic number is the number of protons in a nucleus. So from this point of view, I can tell you that I've got 232 protons and neutrons, and 90 of them are protons. If I was to separate them out, you could figure out how many neutrons there are. That's not what I'm asking you to do now, but you could. So TH, by the way, if you look at the periodic table and you look for something that's got an atomic number of 90, that's the way the periodic table is arranged, by atomic number, as in how many protons has it got, then you'll find that that substance is thorium. Okay, so it's got the symbol TH, so this is thorium. We started off with thorium. So let's imagine it undergoes alpha decay, and here I've said use the structure section of your sheet. I'd have physically given you that sheet if we're in a lesson, but obviously we're not. So using the structure section, if you think about it, alpha decay was 2 protons and 2 neutrons. So I've started off with thorium, and 2 protons and 2 neutrons have been ejected from the nucleus of that, thorium nucleus. We need to figure out what kind of changes that's going to make. So let's have a quick look at this. It starts off with 90 protons and 232 protons and neutrons. That's how it started off. I've just taken those numbers straight from there. Mass goes down by 4, atomic number goes down by 2. That's interesting. Why are those changes taking place? Well, if you think about it, the mass goes down by 4 because alpha decay is when it gets rid of 2 protons and 2 neutrons. That's 4 particles with mass. So 4 particles with mass have just been ejected from the nucleus, so its mass number has gone down by 4. Its atomic number goes down by 2. Well, it started off at 90. Remember, two of those 4 particles that had mass were protons. So that is going to affect its atomic number or its proton number, so it goes down by 2. So that then changes these two numbers. So it now has 88 protons and 228 protons and neutrons, because if you look at it, 90 minus 2 is 88 protons, and then 232 minus 4 is 228 protons and neutrons. So if I was to rewrite this out now, as in something's got a mass of 228 and it's got an atomic number of 88, I'll find out that that isn't thorium anymore, that's something else. Now, I'm not interested in the mass number to find out what something is. If you've got a periodic table, you could use one on your phone, or you could use one on an app or something, you could go on Google and find it there, you could use one in your planner. There's all sorts of places you can find it. But let's just have a quick look. It's got 88 protons. So if I look for something with the atomic number 88, I find that's radium. So thorium, if it undergoes alpha decay, actually becomes radium, okay? And you could have figured that out yourself if you had a periodic table. It might be worth pausing the video and getting a periodic table now, by the way, however you want to do it. And that's really convenient because it's just in your phone then. Right, let's stick with thorium, but this time we're not interested in alpha decay, we're interested in beta decay, okay? So I've still got thorium, and it's still got the same mass, 232, and it's still got the same atomic number, 90, okay? So we're ignoring everything in yellow now, we're acting as if this is a new thing. So we've got thorium, it's got a mass of 232, and it's got an atomic number of 90. again, using the structure section of your sheet, if you think back to the previous slide, beta decay is when a neutron turns into a proton and electron, and the electron gets ejected. Okay, so let's have a quick look at what difference that makes to the actual substance that we started off with. So it starts off with 90 protons and 232 protons and neutrons, exactly like it did before. Okay, so that's our starting point. It's the same. This time though, the mass stays the same and the atomic number goes up by 1. Let's think about why that is the case. So I've gone from, the mass stays the same, let's do that first. I've gone from a neutron that has a mass of 1, and it's turned into a proton that also has a mass of 1 and an electron, and it's got rid of that electron. Now we appreciate that you're probably thinking, hang on, you told us electrons have mass. They do have mass, you're right, but it's so minuscule in comparison to the proton and the neutron that we don't even really count it in this process of working out if there's a difference in mass. So the neutron becoming a proton, that's gone from a mass of 1 to a mass of 1, and it's lost like the mass of an electron, which is 0.0005 in comparison. So just ignore it for the time being. It's not worth trying to figure that out. So if it's gone from a neutron to a proton, the mass stays the same. So later on, if I'm asking you to write this out, if I said thorium underwent beta decay, you'd go, right, well the mass was 232, so it's still 232, so I'll just write that down straight away. The atomic number though, which is what you'd need next, goes up by 1. Why has that gone up by 1? Well, it started off with 90 protons, and then one of the neutrons that was sat in the nucleus went, you know what, I want to be a proton as well. So it turned into a proton and electron. So its proton number just went up by 1. So if I was to actually write this out, if I was doing this in an exam, I'd go, right, thorium's got a massive 232, it's undergone beta decay, so it stayed the same, so 232, and its atomic number goes up by 1, and it started off at 90, so it's 91. I've not got thorium anymore, its atomic number is changing, and therefore the substance that we've got has changed as well. So let's just have a quick look. So I said 91, didn't I? Let's find what's got an atomic number of 91. That is protactinium. Okay, so thorium, if it undergoes beta decay, becomes protactinium because it's now got 91 protons and 232 protons and neutrons. The last one is dead easy, to be honest with you, and I'm only going to mention it once, and then we're not going to do any more about it in this lesson because, well, there's not much to remember. If I were to have thorium again and it underwent gamma decay, then, well, let's have a look what happened. So again, you think about the structure section in your sheet. Gamma was just a wave, it wasn't a particle. So I started off with 90 protons and 232 protons and neutrons, and everything stays the same. No particles are given out. Okay, so it gives out a gamma ray but loses no particles, so it's still got 90 protons and it's still got 232 protons and neutrons, and therefore, if I look that up, I don't need to because it's there already, 90 protons means it's thorium. So if thorium undergoes gamma decay, it stays as thorium. But it's really important to know, just because it's not gotten rid of a particle, and it hasn't changed into another substance, it doesn't mean it stays as unstable as it was. By getting rid of energy as a gamma ray, it's still lost a little bit of energy and therefore become a bit more stable. Okay, that's important to remember. So these are the three things that could happen then to a nucleus. They could undergo alpha decay or beta decay or gamma decay. And I should point out that I've used the example of thorium here, but I could have started with anything that is unstable there. Alright, so it's not always, alpha decay isn't always going to turn it into, radium, and beta decay isn't always going to turn a substance into protactinium. It depends what you start off with, okay? The changes are the same in terms of the number. So for alpha decay, the mass always goes down by 4 and the atomic number always goes down by 2. And for beta decay, the mass always stays the same, but the atomic number always goes up by 1. And then in gamma decay, there is no change in terms of the atomic number or the atomic mass. So let's get you having a go at this yourself. I appreciate I've put question 1 and question 1 here. Don't worry about it. It's obvious which one's which. The questions are relevant, so it's fine. What is formed when radium undergoes alpha decay? Is question 1. And then question 2. What is formed when radium undergoes beta decay? Okay, that is radium, isn't it? Let me just check. That's not radon. I always get them confused. Yeah, it's radium. Good. So have a look at those two. Rewind the video if you need to think about the structure and what happens when it undergoes alpha decay and beta decay to the atomic mass and the atomic number. And all you need to do now, just on a scrap piece of paper or on your phone or wherever you want to do it, just think, right, I started off with 228 and 88 for radium. What happens to the mass number for alpha decay? Right, I'll write down the new mass number. What happens to the atomic number for alpha decay? Right now, I'll write down the new atomic number, and then I take that atomic number and I go to my periodic table and I find out what substance that is with that atomic number. Okay, so pause the video. Don't take more than 2 minutes per question. Just dead quick. Like I say, rewind if you need to. So just pause the video now and give that a go. Okay, let's go through those answers then. So I started off with radium. That's got an atomic mass of 228 and an atomic number of 88. What happens if it undergoes alpha decay? So let's have a look. So alpha means it loses 4 from its mass, which is the biggest number, not the number at the top. Remember, the position of these numbers is irrelevant. In different periodic tables, it's the wrong way around. So sometimes, not the wrong way around, it's just a different way around. So on some periodic tables, the mass might be at the bottom or the top or wherever. So don't go off, oh, it's the number at the top, just go off, the mass is the biggest number, which makes sense because it's a combination of all the particles with mass. Of course, it's going to be the biggest number. So it started off with 228, it loses 4 from its mass, the biggest number, and 2 from its atomic number, which is the smallest number, so 2 from 88. So it turns into something with a mass of 224 and an atomic number of 86. And if you use your periodic table, the element with the atomic number 86 is radon, okay, which it says there. But I'm just showing you can use a periodic table to figure this out. Right, the next question. What is formed when radium undergoes beta decay? So let's have a quick look. So in beta decay, it means it loses 0 from its mass. Remember, a neutron's just become a proton and electron. The number of particles with mass hasn't changed. Okay, so it loses 0 from its mass, which is the biggest number, and adds 1 to its atomic number, which in this case is the smallest number. So it turns into something with a mass of 228 and an atomic number of 89, because obviously 88 has gone up by 1, it's gained an extra proton. And using the periodic table, it says it's actinium there, let's just check. Atomic number 89 is just there, and that is actinium. I don't think you can even see my phone there, but hey ho. So that is what I want you to understand. Any substance that you are given an exam, they might say it undergoes alpha decay or beta decay or gamma decay, and you need to tell them what it's turned into and justify it. Okay, so you need to show your process of, right, well, alpha decays 2 protons, 2 neutrons, that it's ejected from the nucleus, so the mass goes down by 4, the atomic number goes down by 2, and then I've looked at my periodic table that's actually given to you in an exam, by the way, and I figured out what's got the atomic number of whatever it is I've just worked out, I've just calculated. Okay, and then obviously beta decay, just to repeat myself again, the mass doesn't change, the atomic number goes up by 1, and you just, again, always concerned with the atomic number, not the atomic, so much the atomic mass. You don't look for the atomic mass on the periodic table, you just look for the atomic number, and it'll tell you what your substance is. Right then, this is a decay chain. Pretty interesting to note that just because something decays, let's say, in this case it's thorium again, let's say something decays and it undergoes alpha decay or beta decay, whatever it is, or gamma decay, and it gets rid of some of that excess energy. That doesn't mean it's stable. It's more stable than it was, but that doesn't mean that it's stable. So you could start off with one unstable radioisotope that decays in using whichever form it wants, and it ends up making another unstable isotope. And guess what? That unstable isotope that's just made is going to decay again, and it'll keep happening until it gets to something that's stable. And you can see that's what's happened here. This is called a decay chain. All right. So I'm going to do the first. I'll do the example one with you, and I'll do this first one with you, and then I want you to do the rest of them yourself. Okay. So let's have a quick look at what's going on here. Thorium started off with 232 atomic mass and 90 atomic number, and it underwent alpha decay. Now, if this box is blank, I'd want you to fill it in the following way. Okay, so it says it's alpha decay. It says down here it loses 4 from its mass. So 232 minus 4 is 228. Great, we got that bit right. And it says it loses 2 from its atomic number. Well, it was 90 minus 2 is 88, and guess what? They got that right as well. And then all you need to do is go to your periodic table, find something with the atomic number 88, and that is radium. Okay, so they've got that first one right. So let's just do this one by ourselves and no help from them. So we've got radium, it's got a mass of 228 and it's got an atomic number of 88 and it undergoes beta decay. So let's have a look at this. Beta decay, it loses 0 from its mass. Stop there. Its mass was 228 and I've just been told it loses 0 from that. Alright, so I'll just rewrite 228 then. Its mass hasn't gone now. You might want to play this at double speed because I'm having to use a mouse rather than a graphics tablet, so I'm writing quite slowly. Right, so its mass has stayed the same. Great, halfway done for this now. What's the other one? It adds 1 to its atomic number. Okay, well it was 88, and it's added 1 to that, so let's write 89 there, because that's 1 higher obviously. And then I go to my periodic table and I find something with the atomic number 89, and that is actinium, AC. So I'm just going to write A, C. Okay, so we've done a couple of steps in this decay chain already. What I want you to do now is pause the video and fill in the rest of those. Please use the green box at the bottom. You need to get into your head that alpha decay means 4 from the mass, 2 from the atomic number. Beta decay means the mass stays the same and the atomic number goes up by 1. And gamma decay means there is no change. Now, I'm not going to lie to you, there's no gamma decay on there. Whoever made this worksheet didn't put it in, but it doesn't matter. All you're interested in is alpha and beta, basically, because you'll remember that gamma, there's no change. So pause the video and take as long as you need to get this done. Okay, I don't mind how long you spend on this, it's using your own time. Pause it, try it. If you want to rewind back and try and go through that again, I'm happy for you to do that. So just fill in those blanks, pause the video now, and I'll come back to you in a second. Okay, let's crack on then. So the answers then that you should have in this decay chain. It says actinium undergoes beta decay. Beta decay means it loses 0 from its mass, so 228 is still 228. And it adds 1 to its atomic number, so 89 now becomes 90. I have a look at my periodic table. What's got an atomic number of 90? And it is thorium, TH. So I'm just going to put a T and a H there. Right, thorium undergoes alpha decay. So let's have a look at that. Alpha decay, it loses 4 from its mass. Well, 228 minus 4 is 224. And it loses 2 from its atomic number. 90 minus 2 is 88. So let's have a look. The element with the atomic number of 88 is radium, which is Ra. Good. Chugging along here. Right, radium undergoes alpha decay again. Alright, so alpha decay, it loses 4 from its mass. It was at 224, so now it's 220. And don't worry about the mass. The mass doesn't determine what substance it is. Okay, so I could have, for example, I could have thorium 90, which means it's got an atomic number of 90, but it could have 228 mass, it could have 226, it could have 228, it could have 229, it doesn't matter. The mass makes no difference, okay? We call those isotopes of elements. And there's loads of them. It's like, think of it like slightly different versions of the same element. It's still thorium, but it's different because it's got a different mass. We get the same thing with, you might have done this in a previous lesson, hydrogen. There's isotopes of hydrogen as well. So you get like deuterium and tritium. They've still got the same atomic numbers, it's just their mass is different. So they've got very, very similar properties to hydrogen does. Anyway, right, off on a tangent there. So radium has undergone alpha decay, its mass has gone down by 4, good, and its atomic number, it says, goes down by 2. So 88 is now 86. Straight back to our periodic table, what's got the atomic number of 86? Radon. So I'm going to put the symbol for radon in there. N. Okay, radon undergoes alpha decay. Alpha decay means it loses 4 from its mass. So 220 is now 216. It loses 2 from its atomic number. That was 86, so now that's 84. Right, atomic number 84, let's have a wee look, is polonium. So I'm going to put the symbol for polonium in there. Okay, so polonium undergoes alpha decay. Alpha decay means it loses 4 from its mass. So 216 is now 212. And it means it loses 2 from its atomic number. So 84 minus 2 is 82. And then I'll look back on the periodic table. What's got an atomic number of 82? That is lead, Pb. Pb, oh my writing's a bit dodgy, isn't it? Okay, so then we've got lead undergoing beta decay. Just wrap your head around this. So far, this decay chain, it's not become stable. It is still unstable. It's trying to get to a substance that is stable, okay, which is related to the size of the nucleus as well. So beta decay for lead. Beta decay says it loses 0 from its mass. Its mass was 212, so I'm going to keep that 212. And its atomic number is 82, and it says its atomic number goes up by 1, so 82 becomes 83. Let's go back to the periodic table. What's got an atomic number of 83? Bismuth. Bi. Okay, so bismuth then undergoes beta decay. We'll go this way. You could go either way, it doesn't make a difference. Bismuth undergoes beta decay, which means it loses 0 from its mass, so its mass stays at 212. And its atomic number goes up by 1, so 83 becomes 84. And then atomic number of 84 is just there. We're back to polonium again. So capital P, lowercase o. And this is the first opportunity we've had to kind of check our work to make sure we've got it right. If the alpha decay of polonium leads to lead now, we know that we've got this decay chain right so far. This one's missing, but we'll find that out in a minute. Right, so polonium undergoes alpha decay. Alpha means it loses 4 from its mass. Well, 212 minus 4 is 208, so we've got that bit right. And it loses 2 from its atomic number. Well, 84 minus 2 is 82. Smashed it. So we've got this part of the decay chain right, definitely, because we know that polonium undergoes alpha decay to become lead in this with this mass and this atomic number. Okay, so that bit's definitely right. Let's just finish this off then. So bismuth undergoes alpha decay. Well, its atomic mass is 212 minus 4 is 208. And then its atomic number, what we do in alpha decay, its atomic number goes down by 2, so 83 is 81. And then I go to my periodic table, atomic number 81 is thallium, Tl. Right, let's just check if we've got this bit right. So if thallium was to undergo beta decay, let's have a quick look. It says beta decay, it loses 0 from its mass, so 208 stays at 208. Tick, we got that bit right. And it gains 1 to its atomic number. 81 becomes 82. We got that right. So that is what the decay chain for this looks like. Hopefully that's not too confusing. I've got something I want you to do now. It's not so much homework as it is extension work, because you're already doing this at home in the first place. So what I want you to do now is to look up the generic equations for alpha decay and beta decay. Okay, so hopefully you know what a generic equation is. It's one that you can remember up here, and then you can slide numbers in. So let's say you're in an exam, you just remember that one generic equation, and you can put the numbers in from whatever they've given you, and it will give you the right answers. Okay, so the generic equations for alpha decay and beta decay. If you don't know what I'm on about with a generic equation, you've probably used one before in the hydrocarbons topic. Okay, so the hydrocarbons topic, when you're doing alkanes and alkenes and all that, you're given a couple of generic equations there. Like the alkane one is CnH2n plus 2 for figuring out how many hydrogen atoms would be attached to carbon atoms in an alkane chain. And you can use that CnH2n plus 2 in an exam. You just remember that, and you can stick other numbers in it, like you give in an exam question. And it helps you answer the question. So you just need to look up the generic equations for alpha decay and beta decay. Right, I'm going to stop that there. Hopefully that's been useful to you. If you've got any questions about this, you can ask them on the Google Classroom, wherever this has been submitted, and your teacher should be able to answer them for you. If I see it, I'll answer them. Or you could drop us an email, but hopefully that's not too bad and it makes sense. It is a bit confusing the first time you do it, but as long as you remember this green box at the bottom, you're good to go. Okay? Yeah, I think that's it. Okay.